You ready? No? Well, is this all? Do you have this many people now? Oh, okay. Marshall, can you count this? How many pages they have? And count the number of students. If it's not more than, if it's less than number of students, please make a photocopy of this, okay? But I think you should have 65. What? Very likely, I think it is. But you will get 10. Last time, some people didn't get 10. And I'm kind of sad. And I think he or she may sad too. So this time, I will make sure that you get 10. Okay? You should get maybe 8, 9%. Should not get less than that. So last time we go through the derivation. At the end, we get this equation, right? And when I put everything in, I get 38.778 something. So that is the isothermal flow equation. You recall this? Behind set, what is it? Yeah, with cat, yes. What's your name?
Brian.
Brian? Where did we get this from? What is the starting equation? Did you come yet? 2 days ago?
Yes.
Yes? Okay. We start from somewhere. What is that? Mechanical energy balance. Yes. And we make some assumption. One of the assumptions is F is not a function of X or F constant. So what we have is for isothermal flow. Okay. Generally, what is isothermal flow? Isothermal flow. What is the term isothermal? Constant what? Constant temperature. Correct. So we have isothermal flow. Okay. Kai, what's kind of bad? Kai, is that you, Kai? I will call you for next question. So we assume that F is constant. When we assume that F is constant, this is quite valid actually for gas flow. Let's think about it. When we have isothermal flow, temperature is constant. When temperature is constant, viscosity stays constant, right? And from continuity equation, we know that rho times U equal to constant. Rho multiplied by U multiplied by A is constant, but we don't have the change of cross-section area, right? So rho U, velocity multiplied by density, is constant at any location. No gas leak, no gas accumulation. Make sense? So when we look at Reynolds number equation, viscosity is constant because we have a constant temperature. Diameter is constant because our pipe doesn't have diameter change, and rho U become constant from continuity equation. So basically for isothermal flow, we can roughly assume that Reynolds number is constant. Okay. And we know that friction factor is really a function of Reynolds number and roughness, right? So if roughness stays the same everywhere, and Reynolds number is the same everywhere, so friction factor can be assumed to be constant. Okay, you got that? Today we will finish this pipeline and parallel pipe calculation, and about 4, 5, 6 p.m. on, you will get some homework. If you don't get homework today, you will get tomorrow. Okay, so that's homework is for flow in the pipeline and metering. Okay, right now we have F constant for isothermal flow, and I show you that this makes sense. Okay, then we say no work done on the system, no compressor in the middle. Okay, in the pipeline, no compressor. Horizontal flow, we don't worry about change in the angle, inclination angle, anything. We said horizontal flow. Z is not a strong function of pressure. So if you recall, in last lecture, we do something like from equation of state, we have this term, right? dP over P equal to d rho over rho. To do this, we said dz go to 0 or compressibility factor doesn't change much, or maybe ideal gas. That's the assumption when we derive this equation. So by the way, this equation is really important. Okay, it's the basis for many empirical equations that you will have later. Z is not a strong function of pressure or ideal gas or short section of pipe. We look at this graph and we said, okay, close to atmospheric pressure, compressibility factor doesn't change much for some temperature, but sometimes it changes a lot, right? So that equation that we have, then it is for kind of ideal gas. So it's like theoretical value. We may not be able to use it directly because in reality we have a long gas pipeline, right? And with the long gas pipeline, compressibility factor will change with pressure. If we still want to use this equation, we can do by use it for small pipe length. So it may not work for 100 mile pressure drop calculation, but if you use just like 0.1, 0.2 mile, you can get pressure drop calculation, get new pressure. From new pressure, we can update compressibility factor. Okay, here's the equation to use to estimate Z bar and P bar. Through the derivation, at the end we have this term, Z bar, T bar over there. So there has to be the way to calculate average temperature, average compressibility factor. Here it is. We use this formula. So for something that less than 100 psi, we just use 1 over 1 plus some coefficient multiplied by P bar. Or this one. That one is for pressure more than 100 psi. And P bar is the average between 0.1 and 0.2. Okay. If you also recall, when we do the derivation, we change from P rho 1 over P1 to be later rho bar up over P bar. Okay. So this equation, you may need to know, you may need to do some kind of iteration. So we need easy equation for you. For AGA, American Gas Association Isothermal Flow, we have further approximation for the transmission factor 1 over square root F. So we just assume 1 over square root F equal to that. Okay, just the first term in Coburg equation. So this is to not do iterative method. But you can do that, right? Last time you pass the quiz on that. Most of you pass the quiz on that, so you can do that. So we have equation. This time I have another term. Let's take a look at the rest. This is the same as before that we have earlier. TB, PB is the best pressure temperature, same that we have earlier. E is 1, right? About 1. This part is just 1 over square root f. So basically, ATA equation is this equation, but express 1 over square root f with 4 log base 10 of 3.7 over epsilon d. That. And we have another term, elevation term. Elevation term has to do with height at 2 different locations. Usually, it is small, unless you go uphill like several hundred feet. Okay. The reason that this term is small because gas density is small. So if we do the calculation for liquid, we may not be able to neglect it. For gas, when you neglect it, it should be fine most of the time, unless you go uphill 500 feet or something, then we have to include that term. So that's the equation. This equation is not the equation that you will actually use. Because O'Neill, why do you think that is? Why don't we use isothermal flow equation for pipeline? We just don't use it. Why is that? OP? Any particular reason that we don't want to directly use isothermal flow equation?
Because the temperature is not constant.
What do you see, OP?
Because the temperature will remain constant.
Because we don't have isothermal flow in the unless it is a pipeline that we don't insulate, then it is isothermal flow. Temperature equal to environment temperature. Most of the time, temperature inside is not the same as environment temperature. There's a temperature drop, and we may probably insulate it or bury it or something. So most of the time, it's not isothermal flow. If we use it in the facility, we have pipe buried underground. It's not isothermal flow, right? It is adiabatic. You remember adiabatic? Adiabatic Q equals 0. So we need empirical based equation, which is easier. No iteration. Number 1 that we take a look is Weymouth equation. Weymouth equation is good for flow in production facility. Okay? This is on the quiz. How many copies do you have? 63. Okay, it should be fine. So memorize this. Weymouth equation is not for long cross-country pipeline. It is for flow in production facility. A short pipe. Okay? Short pipe. Weymouth equation is good. It is good up to 12 inch. Above 12 inch, don't use Weymouth equation. So Weymouth equation is for flow in the facility, short pipeline. Okay? Let's take a look at it. We have a constant in the front. This one is new, right? Previously we have 38.77. We have these two terms, same. And we approximate 1 over square root of friction factor to be just dependent upon diameter, d to the power of 1/6. So we absorb or merge this term with that diameter. Previously we have d over 2.5, right? d to the power of 2.5. That's theoretical isothermal flow. Weymouth express 1 over square root f in a different form and have another unknown constant in the front, put d over there, and then done. What in the quiz is good for a short pipe gathering system. Okay, that's in the quiz. This is not in the quiz, but you should know that degree of error increase with pressure. Okay, so when pressure go up, you can have more error from your Weymouth equation. It must be fully developed turbulent flow in the sense that we have, what do we say? Okay, let's go to the next page first. Q over here. Q is cubic foot per day at base pressure, base temperature, or standard condition. If your standard condition is 14.73 psia, put that over here, and you use 60F, convert that to Rankine, put it over here. So that's Q. P is psi. A, we use psi A because this is derived from equation of state, and in equation of state we use psi A. T, Rankine, not Fahrenheit. Okay. D, this small d is inch. L sub m, mile. Okay, in mile. Okay, that's L sub m. And 1 mile is 5 to 80 feet. Okay, 1 mile is 5 to 80 feet. That's 1 mile. Put everything here in. So if we know the flow rate, we put the flow rate in. We know base pressure, base temperature, so that's standard cubic foot per day. We put average temperature that we expect, maybe 70F. Compressibility factor, maybe you may have to use the chart or this equation to be quick. Okay, put it in, put diameter in, then we can get P1 square minus P2 square. You know P1, then you can calculate P2. Okay, so with this equation we can know pressure drop in the facility. Diameter less than 12 inch. So it is based on the measurement of compressed air flowing in pipe from 0.8 inches to 11.8 inches. So this is empirical based. So if you want to use it for 12, not a good idea, maybe. 20 inch, no, not Weymouth. It is for fully rough region. Fully rough region means friction factor is only a function of roughness. Okay, friction factor should be only a function of roughness. Our Reynolds number is very high. If you recall the Moody chart, if Reynolds number, Moody chart look like this, right? So if Reynolds number is high enough, regardless of Reynolds number, friction factor stays the same. It changes only with roughness. Okay, so Weymouth equation good in that part when it is fully rough region. Okay, memorize this for exam. It's not in today's quiz. It should not be used for diameter more than 12. Good for short pipe. Okay, there's another note that I just found from GPSA. From GPSA, it said, do the calculation as usual. Okay, do the calculation as usual. After we get Q, multiply Q from Weymouth equation with 1 over square root Z. This will give the corrected value of Q and will be closer to the measurement from the meter. Okay. That's a recommendation from GPSA. I didn't find this in the Stewart surface production operation. If you want to go with that, in the exam, you don't multiply with 1 over square root Z. That's if you can calculate the Q from Weymouth equation and fine. Okay. Panhandle A is another one. So Weymouth is for short pipe, not cross-country pipeline. Short pipe, you can say 1 mile. 1 mile is relatively short compared to 500 miles. Okay, 1,000 miles. So Panhandle A is for longer length. Okay. This is the equation. We have some constant E, but this time E, the recommendation for E is 0.92. Okay, that's a general recommendation for Panhandle A. Do we use it anymore? Stewart surface production operation book suggests use Panhandle B and don't use Panhandle A at all. Okay. We have P1, P2, same. LM is my gamma. Kai in the back. What is gamma?
The specific gravity?
Specific gravity and equal to 1, correct. That's gamma. So when we find gamma, we do what? Molecular weight of that gas divided by 29, that gives you gamma. Okay. This equation becomes less accurate as flow rate increase. So when flow rate go up, it becomes less and less accurate. That's Panhandle A. Originally from Panhandle Eastern Pipeline Company from early 1940, good for long cross-country gas transmission pipeline. Today, only the Panhandle B is used. That's a comment from Stewart. So Panhandle B is for cross-country pipeline. That's what in the quiz today. Okay? Memorize that. Get it correct. Wrong answer, get -2. Okay? So Panhandle B, just say Panhandle B. Okay? Panhandle B. Whenever Panhandle A can use, Panhandle B can use too. So just your answer should be just Panhandle B. It's for cross-country pipeline. Same Q is same definition. ACFD. Z average compressibility factor, E pipeline efficiency from 0 to 1. F fan friction factor, D is inner diameter in inch. L is in mile. When you have bar on the top, that's the average property. P bar is the average property. Stewart has a little bit more specific recommendation for E value for Panhandle A. Okay. In general, just use 0.92. It's good. But if we want a little bit more out of it, more accurate, we can change E with diameter. Okay, this OD and ID is a commercial pipe size. So let's take a look. The recommendation is E is 0.92 multiplied by another correction factor F sub pan A. Okay, 0.92 multiplied by some correction factor, and correction factor getting from table. Your pipe size will be just only this. Okay, because not every pipe size is available. If we use 2-inch pipe, correction factor is 0.9. Okay, 3-inch still 0.9, 4-inch still 0.9, 6-inch 0.9, 8-inch 0.9, 10-inch 0.9, 12, 13 use 0.9 multiply on top of this. If you happen to have the pipe as large as 26-inch, okay, and use Panhandle A, then that F equal to 1, or E equal to 0.92 multiplied by 1 equal to 0.92. If your pipe is greater than that, like 42 inches, you have 1.07 something. So this is to try to make it a little bit more accurate, okay, for Panhandle A. But Stewart, I use volume edition 2, I think, so they don't write the book together like Arnold and Stewart. No, not anymore. For this part, it's just Stewart. Okay. Panhandle B. Better than Panhandle A. This is for gas. By the way, isothermal gas flow equation is for gas. Weymouth equation is for gas. Panhandle A, Panhandle B is for gas. Whatever we are talking about today is for gas, and it can be used only for gas. Don't use for flow board or something. It's not accurate. Okay. Panhandle B, we have another way for transmission factor, 1 over square root F. Previously, we used 6.872 real number to the power of 0.073 something. Now we use different value. Okay, put it back in, we get another equation. Panhandle B. Panhandle B is for cross-country pipeline. It is more updated than Panhandle A. Stewart recommend to not use Panhandle A anymore. Just use Panhandle B. So E value will depend if it is a brand new pipe, set E equal to 1. Old pipe, but good operating condition, 0.95. Average operating condition, 0.92 on average. If it's favorable, use 0.85. Unit defined as the same as shown in Panhandle A. Okay, that is the equation to use. You like it? In reality, you will use several of them, okay, and select the highest value that it gives you. Okay, comment. Panhandle A and B use the preset value of mu gas. So in the equation that you have seen here, it is valid for viscosity of natural gas. It's a preset value. It's absorbed in the constant, this constant, this constant. Look at this. They don't use 0.5, they use 0.51. Okay? So that is to account for the change in viscosity with temperature and everything already. Okay? So if we cannot change it. Okay? That's one thing to keep in mind. So Panhandle A, B already account for the change of viscosity. E may be adjusted to make the prediction match with the meter result. Then extrapolation can be done. What's that mean? So this means, let's say we have some data. Okay, we try to find out if we build another one, what will be pressure drop, for example. So with the data that we have, pressure drop with velocity or with flow rate, right? We put that data in and try to adjust E that make left hand side equal to right hand side. So with the data that we have, you may find that, okay, E equal to 0.93. Make the prediction of pressure drop match with the pressure drop that we get for a given flow rate. So then we can, for another design, we can use that too. So if we purchase the pipe from the same vendor, and we had experience that with that vendor, E is about 0.97. So when we build it again, we use 0.97. So E can be adjusted. Okay, look at this one. In practice, Panhandle B is used for straight line portion of the friction factor diagram, fully rough. So what is fully rough region? You see that, right? Friction factor change with Reynolds number, but after a while, it's just straight. Okay. In practice, they use it for this part. In theory, it can be used anywhere. Okay, for cross-country pipeline. Neither Weymouth nor Panhandle A and B give the conservative assumption that we can always over-predict the pressure drop. So this means if you use Weymouth, Panhandle B, sometimes it's over-predict, sometimes it can under-predict. Okay, that's a comment. And how do we do? I will put it later. What do we actually do? So you know Panhandle B is for cross-country pipeline. That's in the quiz. Okay, memorize that. And what about another one? Weymouth is for flow in the facility, diameter less than 12 inch. Memorize that. That's in the quiz over there. Okay, next one. Olifant formula. This equation, you have this kind of expression. It's good for vacuum up to 100 PSA. Stewart suggests to use it just 35 PSIG. Okay, so the equation that we use for vacuum pressure is Olifant formula. You don't really need to memorize how to spell this word because in the quiz there's a choice for you to select. You just know that it starts with O. Olifant formula. Okay? Olifant formula is for vacuum. You want to repeat after me? Olifant formula is for vacuum. Do it. Do it, please. It is in the quiz. Okay, next one, split glass formula is for use for pressure less than 1 or about 1. Split glass formula is for pressure about 1. Okay, it's good for just that. Low pressure. This one is also in the quiz too. For pressure about 1, use split glass formula.
Less than 1.
It's not in the quiz?
Less than 1 or above.
Less than 1 or about 1 is fine. In some In GPSA, it says less than 1. In Stewart, it says it's about 1. So I would say about 1 or less than 1. In quiz, I said it's about 1. Okay. So for this particular quiz, when I say which formula, gas flow formula is good for pressure that is about 1 psi, you say split glass. Which formula is for vacuum thing, you say elephant formula. Good. So whoever get less than 10, it's not my fault anymore, okay? Alright, look at this. This question in particular, every time I use L sub M, which is for mine. For split glass, I use just L. Intentionally, this is not typo. That L is infinite. Okay? L here is not in mine, like L sub M. So if you use split glass and then you use this coefficient and you use L, that L is infinite. So split glass formula works best if you have pressure drop less than 10% of inlet pressure. Okay, if the pressure drop is too much, it's not good. So now you know Panhandle A, Panhandle B. So you don't use Panhandle A, you use Panhandle B. If you have facility, flow from facility to gas plant, just use Weymouth. Okay, here's a recommendation. When you have 12 inch and below, Panhandle also valid. Weymouth also valid, right? Use Weymouth and Panhandle B, use both. Select the higher pressure drop case. Okay, that will be the conservative, the best thing that you can do. It's not always that any of them will over-predict pressure drop. Sometimes it's under-predict, okay, so you do both. Weymouth is for small diameter, short run pipe in production facility. Diameter less than 12 inch is for high Reynolds number. Okay, if you use for low Reynolds number, is maybe better than nothing. It gives you something, but maybe not as accurate as it should. Panhandle B, diameter more than 12 is good. It's typically for cross-country pipeline. Moderate Reynolds number is okay too. Okay, what is moderate Reynolds number? 10,000 is that moderate Reynolds number? 20,000 is moderate Reynolds number. You will see the number. Okay, later. Split glass, low pressure application like vent flow. Okay, elephant, vacuum, or something less than 35. And it have the best performance for gamma equal to 0.75 actually. Okay. For this particular quiz, when I say vacuum, use that formula. Okay. And when I say pressure above 1, you have to answer split glass, otherwise you don't get anything. In reality, I think this one, elephant, can be also used for like 1 psi, 2 psi too, because it's also good from 35 and to below 0, right? Below 0 psi. This is a question that you did last time. If you have problem of not getting the right answer, you should try with the given equation. Isaac, seems like you have a good time, right? How was it? Taste good? Sure. Me too sleepy. Let's do something else. So now you know everything for the quiz. Let's do another pipeline. Series, parallel, and loop pipe. What do we do if we put it in series? What do we do if we put it parallel? What do we do if we have this pipe? So I have 1-inch pipe and I have 3-inch pipe. Which one should have more pressure drop? We don't know because it's different length, right? So next to Kai, what's your name? Steven? Yeah. Okay, Steven. For 1-inch ID pipe, let's say 100 feet. Okay, we have gas flow. We may have a certain pressure drop. That's pipe A. For pipe B, let me have 3 inch. So 1 and 3. So the first one is 100 feet. This one, let's say 1,000 feet. 10 times longer than pipe A. Pipe A. This one is B. So Stephen, which one do you think it should have more pressure drop, A or B? There's no right or wrong because I haven't taught you anything yet. But which one do you think? 100 feet of 1 inch ID or 1,000 feet of 3 inch ID? B should have more pressure drop, right? Let's see if that is like what you expect or not. Okay. Who want to read this for me? Isaac, since you go get a coffee, can you read this one for me? Starting from here.
Pipe A is 1 inch ID and 100 feet long. Pipe B is 3 inch ID and Z feet long. Gas flow in pipe A at a rate of X standard cubic feet per day creates the pressure drop of Y PSI. What should be the value of Y in feet that will allow the gas at a flow rate of X standard cubic feet per day to create the same pressure drop as in the case of pipe A, given that the inlet pressure and temperature for both cases are the same. In addition, the Reynolds number is very high, and frictional factor is only the function of epsilon over diameter. Epsilon is 200 micron.
Isaac, what is F sub capital F?
That's frictional factor.
What about epsilon? What do you call epsilon?
Roughness?
Absolute roughness. Correct. Very good. So we have 2 pipes. Pipe A is 1 inch and is 100 feet. Okay, 1 inch, 100 feet. Pipe B is 3 inch, but I don't know how many feet. And I think I said that both of them has the same pressure drop. So what should be the length of 3 inch pipe that will create the same pressure drop as in the case of 1 inch pipe that is 100 feet long? Okay, that's the question. So we will try to find that value, that Z. Okay? And I have the answer for you. The answer is, it's not actually the answer, but the answer is dependent upon the equation that is used in the calculation. If you use Weymouth, you get one value of Z. If you use isothermal, you get another value. If you use Panhandle, you get another value. Okay? So the answer will be changed depending on what equation you use in the calculation. Okay, let's start. Let's find, so this is to give you equivalent length concept. If pipe A and pipe B give you the same pressure drop for the same flow rate, we can say pipe A is equivalent to pipe B or pipe B is equivalent to pipe A. Okay? Let's start with the assumption that we have. We say Reynolds number is very high. Friction factor is only a function of roughness. So we just take the first term in Colebrook equation. We just have that. Good? So that is just the roughness term in Colebrook equation. You remember Colebrook equation is have 2 terms, but we just take the first term. So next, I just copy the equation of isothermal flow equation. So we have constant base temperature over base pressure multiplied by 1 over square root f, which is minus 4 log base 10 of epsilon. This is kind of concerned if you actually use it. Epsilon and number 1 should have the same unit, okay? I didn't have the same unit over there, but later I have the same unit. So I just put it here. And I have P1 square minus P2 square. I have Z T gamma and D diameter, right? So the only difference between pipe A and pipe B is the length and diameter. Length of pipe A is 100 feet. So I put 100 divided by 5,280. When I actually put everything in, epsilon is in the unit of meter. So I convert 1 inch to be in the unit of meter by multiply by 0.04 or 0.02524. So first equation divided by second equation, I get that. Okay. Rearrange it, I get z equal to 100 multiplied by some ratio square multiplied by 3 to the power of 5. 3 raised to the power of 5, or 3 multiplied by itself 5 times, 4 times, we get 243. Calculate everything, I get z equal to 33,000. So 1 inch, 100 feet will give the same pressure drop as 3 inch, 33,000 feet. Okay, so Stephen, your expectation is not correct yet, okay? But now you know that there's 250 times different when you increase pipe diameter just from 1 inch to 3 inch. Okay? Got it? So both of them, 33,753 feet of 3 inch pipe give the same pressure drop as in the case of 1 inch pipe. So we can say 3 inch pipe of that long is equivalent to 1 inch pipe with 100 feet. Okay? They are equivalent to each other. For a gas pipeline of 100 feet and 1 inch ID, what is the equivalent length of this pipeline in terms of 3.0 inch? Answer for me. Next, Ashley. So I have 100 feet, 1 inch ID. What is the equivalent length in terms of 3.0 inch?
33,753.
Okay, that number, right? Because both of them are the same. For a gas pipeline of 33,753 feet and 3 inch ID, what is the equivalent length of this pipeline in terms of 1 inch ID? So next, Haley.
100 feet.
100 feet. No problem, right? Because we already do the calculation. For a gas pipeline of 33,753 feet and 3 inch ID, what is the equivalent diameter of this pipeline in terms of 100 feet length? Megan?
1 inch.
1 inch. So we can have both equivalent length and equivalent diameter. Okay. So next to you what's his name? Eric. Eric something, okay. Eric, if I have, okay, let me ask you this question. For a gas pipeline of 3 inch and 33,753 feet long, what is the equivalent length of this pipe in terms of 2 inch ID?
I don't know.
Is it 100? No, it's not 100. Is it longer than 100 or less than 100?
It'll be longer.
Good. Okay. So 33,000 feet or 3 inch equivalent to 100 feet or 1 inch. And it should be equivalent to something that longer than 100 feet for the case of 2 inch. Make sense? Okay. So now you can answer the equivalent length problem, right? So next to you, Marcos. Okay. So for 100, okay, let's take a look at